Okay, so I kind of want to switch gear now and talk about the representation of SU2, but before doing that, I mean, I was going to, I had hoped that we would have more time, but I want to tell you something about a little technical thing, which I think just a information rather than a proof, which has a property of the Lie algebra, which has to do with that, something called a Cartan metric. So on a Lie algebra, you can define a metric, and that metric is defined to be the trace of the generators of the adjoint representation. Okay, because of the property that this is a, trace is a cyclic property, this means that it's a this is a symmetric matrix, right? So using this, you can define structure constants which are all downstairs by lowering the upstairs index. Okay, so these are, and another thing you can show and it's for compact Lie groups. That FABC, that is the structure constant, are completely antisymmetric. Okay. So meaning that any odd number of permutations of the indices will give you a minus sign. So another way of expressing this is FABC is the same as FABC when the indices have been antisymmetrized. Are you familiar with this notation of antisymmetrization?
No, I haven't seen it before.
Okay, so yeah, you'll see that suppose you have a tensor, say a rank 2 tensor. Okay, so AAB. Then you can construct a symmetric tensor out of them, say S symmetric AB, which is half A of AB plus A of BA, right? So even regardless of what does if AB has any symmetry or not, this object is symmetric, right? So this is also written as a this sort of bracket AB. This means symmetrization. And here you can also find another tensor which is antisymmetric in the indices, which is you get AB minus BA, A of BA. And this is often written as A of AB, square brackets, okay? And if you have 3 indices, say A, B, C, then it will have 1 over factorial of 3, and then you will have A, B, C plus A, B, C, A plus A, C, A, B plus A, well, then there'll be a minus sign, right? Because, so then you have so these are the even permutations of the first term. And for the odd permutations, odd number of permutations, you have to introduce a minus sign. So that will be, for example, A of A, CB, then A of CBA minus A of BAC. Okay, and this goes on for higher order. So when I say that f of ABC is equal to f of ABC antisymmetrized, that means that these indices are already antisymmetrized. Okay? And this is basically why for SU2, we instead of writing ABC, we write ABC. Okay. So it's all downstairs and it's completely antisymmetric. So in other groups, and we shall see SU3 explicitly, the structure constants are not, of course, the epsilon tensor, but they're still antisymmetric objects. Okay. Any questions so far?
Do all antisymmetric objects have can they be expressed in terms of epsilon?
No, that's a very good question. No. Yeah, no. So the idea is that, so this is a three-dimensional object, right? Because the epsilon tensor, the completely antisymmetric A, B, C, this takes three values, right? So in 4 dimensions, this object doesn't exist, right?
Yeah, that makes sense.
So, but for example, you can have stuff like F123 is so you will see that for SU3, for SU3, which is an 8-dimensional group, right? Because its dimension is 3 squared minus 1, so it's 8. So so it'll have FABC, which will have like F123, F124, stuff like that. And they will all be antisymmetric. But some will be 1, some will be half, and stuff like that, okay? So I'll give you examples of that. So what I'm trying to say is that if you're in 8 dimensions and you have a rank 3 tensor, which is where the indices can take 8 values, it cannot be equal to epsilon ABC, right? But the more interesting question is that if you are in 8 dimension, what about this thing? Is this equal to okay? Now that's an interesting question, and the answer to that, I believe, is yes. If it's if the number of dimension is equal to the number of indices and it's a completely antisymmetric tensor, then up to some constant, it'll be that the corresponding Levi-Civita in that dimension. Okay.
That's interesting.
Yeah, I have not proved this, but that's what my gut feeling is telling me. Yeah, actually, I think it's not hard to prove. Yeah, it's actually not hard to prove that. Okay, so any other question?